Okay, YouTube, in this video we're going to take the process we've been using to solve linear systems with two variables and extend it to three variable equations, but with application problems. And so I just want to show how this process is very similar except for just the solving the system part. But in terms of setting this up, it'll be very much the same thing. So let's go ahead and take a look at this problem here. We'll read through it, understand the problem, and then define our variables, talk about what we want to discover here. So it says that on a recent trip to the convenience store, you picked up 2 loaves of bread, 4 bottles of water. So I'm going to underline these: 2 loaves of bread, 4 bottles of water. Okay, 2 loaves of bread, 4 bottles of water, and 1 package of eggs. It says that our total bill before tax was $19. If a bottle of water cost $1 less than a loaf of bread, and a package of eggs costs twice what a bottle of water costs, then how much does each item cost? And so first things first, let's go ahead and define our variables here. But you'll notice that in terms of how this problem is different from what we've been exploring, you'll notice that there are 3 different items here. And what we want to find is the cost per item. So if we're going to measure cost, typically we measure those, at least in the USA, in dollars. So the number of dollars per, I guess, loaf of bread. Okay, so this would leave us with y. I suppose if we're going respectively through the problem here, we say number of bottles or number of dollars per bottle of H2O, so bottle H2O. And then we would say number of dollars per carton of eggs, so a carton eggs. So we're going to leave this up over here in this little box, but what we're going to do is set up our relationships from this right here. And so as we read through this problem here, we look for things to match up essentially in terms of units. And so what I would notice is, for instance, here we have $19, which is a cost kind of number here, and we're using dollars to represent this. And so what we need to do is kind of come up with a cost equation. And so you kind of see clues as you read through this problem. It says you had 2 loaves of bread, 4 bottles of water, 1 package of eggs. Your bill is $19. We tend to see things like this, where if X, Y, and Z already represent the cost of something, the cost in dollars per, say, each of these things, then if we know how many of each we bought, we could come up with our total cost by saying, for instance, 2 loaves of bread. We would take 2 times the cost of a single loaf. That would be the cost of 2 loaves. So 2 times X, or 2 times the cost per loaf of bread there, plus 4 times Y here, plus a single carton of eggs here. This should be our total bill, and what it comes out to be is $19 here. And so our cost equation, this one we were able to scratch together from the first sentence. Now, what you're going to see oftentimes in, I guess, 3x3 linear systems is they're going to start comparing the quantities X, Y, and Z to one another. And so what this means is we're just going to have to come up with, well, 3 variables. We're going to need 3 equations, but 2 more equations in which we relate these to one another. So when we talk about this, it's a good thing we define these. We say that if a bottle of water costs $1 less than a loaf of bread. Okay, so let's go ahead and pick this apart here. When we say a bottle of water, let me switch back over to red here. A bottle of water, what letter were we using to represent a bottle of water? Well, it seems to me that if we look down here, that was Y. Really what we're saying then is that Y cost $1 less than a loaf of bread. So in other words, it is or equals $1 less than a loaf of bread. Well, a loaf of bread, we're using the letter X. So let's be careful here. A lot of people are inclined to write 1 minus X, but when we say 1 less the cost of a loaf of bread, then we would say that, well, here's the loaf of bread. If we take 1 off of that, then that would be the cost of this. So our second equation, what it looks like here, is this. We say, well, that the cost of a bottle of water is 1 less in value than the cost of a loaf of bread. So our second equation is here. But we're also told that a package of eggs costs twice what a bottle of water costs. So again, when we pick this apart, because we define these, we could say that a package of eggs, another way to represent this, a package of eggs, pardon me, is the letter Z. So we would say Z, okay, is twice what a bottle of water costs. So we say Z is, that would mean Z equals 2 times what? Well, what a bottle of water costs, and we're using Y to represent that. So our third equation comes out to be this Z equals 2Y. Now this right here, I'm going to put a box around this, and I just want to indicate that this is our system right here. And we can go solve this system. It's a 3x3 system. But also what I want you to notice, essentially, is that this is already in a pretty unique form. So in terms of solving this, one really kind of, I guess, common thing to do is to regather ourselves here. So that is to just take our variables and put them all back on the left side of this equation right here. And so if we were to do this, then I suppose we would say that our first equation would be 2x plus 4y, okay, plus z is equal to 19. If we were to bring this x now back over to the left side here, and we realign things, we would really have a negative x, okay, plus a single y, plus no z's, and that would be equal to a negative 1 on the right side. And then in our last equation, as we bring this the 2y back over, it would be a negative 2y, okay, negative 2y plus a z would be equal to, well, there would be nothing left on the right-hand side of this equation right here. And so I suppose that, in terms of solving this, what we want to do is have two equations in two variables. So I guess, one thing that I could say here is this. I already notice that this has just an x and just a y in it. So perhaps what we could do is we could use these other two equations right here to also cancel out z in those two equations. What that'll do is it'll give us another equation that just has x's and y's left over. So with respect to these two equations here, we have 2x plus 4y plus z is equal to 19. That's our first equation. And then our third equation, negative 2y plus z is equal to 0. What we want to do is go ahead and solve this for the value, or go ahead and cancel out the value of z here. So what I'm going to do is I'm inclined to take this whole second equation times a negative 1, which would give us first equation, 2x plus 4y plus z is equal to 19. But the second equation would now become this positive 2y minus a z, pardon me, is equal to negative 1 times 0, which is 0. So adding these together, our goal was to cancel out z in this, because what we get left with now is adding these up. We get 2x plus 6y, and we add up 19 plus 0, we get 19. I'll put a box around this as well. So the cool part about this is now from our original system that we've rearranged, we could essentially say that we have two equations and two variables. Then we could set up a new system, okay, with just our two variable equations, which were negative x plus y is negative 1, and 2x plus 6y comes out to be 19. So solving this system here, I suppose addition method would work very well with our x's if we were to double everything in our first equation and rewrite this system. We would end up with this right here. Oh, I don't have a room here. We give it a negative 2x, okay, plus a 2y equals a negative 2, and we would get a 2x plus 6y equals a 19. Adding these up, I suppose we end up with 8y equals, now adding these together, we get 17 right here. And so what we end up with is solving for y now. I suppose we could divide both sides by 8, and what we would get is that the value of y is equal to 17 eighths. Okay. So now that we know the value of y, what this is going to allow us to do is plug this back in and solve for the value of x. And so we know that, say, the second equation here was negative x plus y equals negative 1. If we were to now plug in this value of y right here, and say this equals negative 1, we get 17 eighths, really. Then we would say negative x equals negative 1 minus that 17 eighths if we subtract 17 eighths from both sides. So what we're going to need to get here is a common denominator. Essentially, we get negative x is negative 8 eighths minus 17 eighths. What we end up with really is negative 25 eighths. So if negative x equals negative 25 eighths, then positive x equals positive 25 eighths here. So now we've found x. Now we've found y. What we want to do is go find z. Well, the interesting thing about this is we don't have to plug it back into this original equation. If we're really after the value of z, then maybe what we could do is plug it back into this equation, or even better, this equation here. And so we could say if z is really equal to 2y, then z must be equal to 2 times 17 eighths. And so what we end up with here is this, I guess if we put 2 over 1 and cross reduce, we get a 4 and a 1, we get 17 fourths. And so I'll put a box around this as well. So the one thing we were seeking was the cost per item. Well, let's do this. Let's go ahead and organize our ordered triple here, our solution. And so we were able to determine that the value of x here, the value of x, I've got that down here, is 25 eighths. Y was 17 eighths. I'm going to write this out here. We have 25 eighths, 17 eighths, and we also have that the value of z here is 17 fourths. So one thing that we want to do, of course, is interpret our results. And so to put these back into the context of the problem, these were the number of dollars or the cost, okay, per item. And so as we look at this here, we say, well, that doesn't really make sense to talk about cost as being those things. When we talk about money, it would probably make most sense to go ahead and get a decimal value on these right here. So if we said 25 divided by 8, okay, and 17 divided by 8. And we were to say, 17 divided by 4. What we really dig out is that our solution values are these. We would say, looking back at this, I'm going to round off to the nearest penny. We have about $3.13, $2.13. So 3.13, 2.13, and I suppose we got 4.25 here, 4.25. And so what we would say is then the value, okay, the value of a loaf of bread is $3.13. Okay, the cost or the number of dollars then for a bottle of water is $2.13. And then we would say that a cost per carton of eggs is $4.25 in the context of this problem. And it'd be pretty easy to go back in and plug these in for these values that we see here on the left and make sure that we actually do indeed come up with $19 for our total bill, but also that they compare to themselves in this way. Cheers.